Hi, I'm Chanh. Today, I would like to introduce our work, DynamiTe, for dynamic termination and non-termination groups. This is a joint work with Timos, Antonopoulos from Yale, Parisa, Fathololumi, and Eric Koskinen from Stevens, and ThanhVu from UNL. Termination, aka the halting problem, is an important problem. In the last 2 decades, there are many powerful static techniques and tools for proving termination, non-termination, or proving both at the same time. However, the techniques could not handle well programs with complex behaviors like nonlinear or when shortcut is not available. Besides static analysis, we also have dynamic analysis, a technique which lost only a few concrete executions to infer reflexive invariance. The technique scale well to large and complex programs, and tools are available. Although dynamic techniques are unsound in general, they seem to fix the above problems. Then a research question comes up. By observing the runtime behavior of a program in a finite amount of time, can we use dynamic analysis to predict or prove the program termination or non-termination? Let's illustrate the problem with two nonlinear programs, B1 and B2. They are adapted from the F equals square root program on the right-hand side. Because of the nonlinear regression in the loop condition in B1, B2, it is not easy to determine the termination of B1 and B2. However, the square root program and B1, B2 share a nonlinear invariant t squared plus 2 times t plus 1 minus 4s equal to 0. Using that invariant, we can rewrite the nonlinear expressions in B1, B2 into s. Therefore, the complicated loop condition in B1 is equivalent to the loop condition as smaller or equal to n in B1 prime. Now it is easier to see that the program terminates since s is always increasing. Similarly, we can see that B2 does not terminate because s is always positive. Here we assume that there are no overflows. A good thing is that program semantics are hidden in dynamic analysis so that the runtime behaviors observed from the nonlinear program B1 and the linear program B1 prime are the same, similar for B2 and B2 prime. There are 3 main steps in dynamic analysis. First, we collect runtime data by running the program on some inputs. For example, to infer the loop invariant of the square root program, we collect the values of the local variables as the location L inside the loop. Second, we analyze the collected data for inferring invariance, detecting security flows, and many more applications. For instance, from the collected snapshot of the square root program, we can derive its nonlinear invariance. Finally, if the shortcut is available, we can validate the results and refine them using the counterexamples from the validation, if any. For example, we can prove that the inferred invariant of the square root program is valid with the right-hand side implication. We follow the 3 main steps of dynamic analysis to decide DynamiTe. First, we instrument the program to collect runtime data from it. Second, we derive termination or non-termination proof from the collected data. After that, we use external tools to validate the proofs and refine the result with counterexample, if any. In the data collection step, we first instrument each loop in the program with a counter on the number of iterations. There is an upper bound, and if the number of iterations exceeds the upper bound, we abort the program. We also instrument the loop with the special method vtrace to collect snapshots at 3 locations, right before the loop with vtrace free, inside the loop with V-shaped body, and after the loop with V-shaped post. Traces are sequences of snapshots, and there are three kinds of them. Base traces collected from execution without loop iteration. Terminating traces, where the location after the loop is reachable, and partially non-terminating traces, where the number of iterations reaches the upper bound. From the collected terminating traces, we follow disjonctive well-founded principle to construct the termination proof in the form of a finite set of ranking functions. First, we construct the transitive closure of the terminating traces. Then we infer a finite set of ranking functions M such that any pair of program space in the transitive closure satisfies at least one ranking function in M. Finally, we use eternal static proofs to validate the set of ranking function M. If the validation is not successful, we use a counterexample to generate new inputs and trace it to infer new ranking functions. Next, we will show how DynamiTe infer ranking function for the motivation example B1. First, we run the instrumented program over random inputs and collect concrete traces. Here for the termination group, we only interested in terminating traces and their transitive closures. Next, we construct a linear ranking function template over the program variables and unknown coefficients. Then we randomly pick a pair of program space from the transitive closure and substitute them into the template constraints. From the ranking constraints 1 and 2, we can find many solutions. Most of them are overfitting to the chosen pair. However, there are only 2 solutions satisfy the optimization 3, which requires that the sum of the absolute values of the unknowns is minimum. For example, we choose to add the ranking function m minus s into the set of ranking function m. We then pick another pair of states that do not satisfy any ranking function in M to infer a new ranking function. However, in this example, all other pairs of states in the transitive closure satisfy the inferred ranking functions. So we move to the validation step. The validation is successful and we return the result. However, if the validation fails, we generate new inputs from the counterexamples and repeat the previous step. Now we saw how DynamiTe derives recurrent sets for non-termination groups. A recurrent set R is a non-empty set of program space such that the loop transition relation is total on it, and the image of the loop transition relation on R is contained within R. If a recurrent set exists, then we can conclude that the loop does not terminate. Using the loop condition as a first candidate, we perform that first search to find a valid recurrent set. When a candidate violates the third condition, we refine it to new candidates for the first search. We use the example on your right-hand side to illustrate how an invalid recurrent set is refined to a valid one. We start with the loop condition t smaller than or equal s squared plus 1 as the first candidate, but it is invalid. We then generate new inputs from the failed group and get new traces. From terminating traces, we use dynamic tools to infer the likely condition for termination. Then we create new candidates from the current candidates and the negation of the newly inferred conditions and add them into the stack. We also infer a condition from the partially non-terminating traces by main loop and consider it as a new candidate. Then we follow the previous step until we can find a valid recurrent state. We also unify the termination and non-termination algorithms into an integrated algorithm for proving both termination and non-termination. We analyze each loop in the program in both order, top-down innermost loop first. If the number of partially non-terminating traces emerge larger than the terminating traces, we through non-termination first. Otherwise, we through termination first. If the result is unknown, we switch the alternative algorithm with the new countersample from the previous algorithm. If the non-termination group is successful, we immediately return the non-termination result. Otherwise, we analyze the next loop in the order. At the end, we return the termination result if all loops in B are proved to be terminating. We implemented the tool DynamiTe in Python with the use of external tools and libraries for instrumentation, symbolic execution, invariant inference, and validation. We evaluated the tool on a linear benchmark from FVCOM, and 4 nonlinear benchmarks include 2 existing benchmarks and 2 new benchmarks with 67 nonlinear programs adapted from the FVCOM benchmark for nonlinear reasoning. On the linear benchmark, DynamiTe through fewer programs and runs slower than the state-of-the-art tool Ultimate Optimizer. However, DynamiTe can prove a program that Ultimate Optimizer cannot. On the 2 existing nonlinear benchmarks, DynamiTe can prove most of the programs, including 4 programs that the other tool cannot handle. On the new termination benchmark, DynamiTe can learn valid ranking function for 37 programs, but the external safety rules can only validate 5 of them. On the new non-termination benchmark, DynamiTe can also prove non-termination of 37 programs. In conclusion, we saw that termination group and non-termination group can be learned from the runtime data of programs. In addition, when shortcut is available, dynamic strategies can be combined with static validation into a refinement framework for better proving termination and non-termination of complex programs. In the future, we plan to support dynamic conditional termination, dynamic non-termination groups for non-deterministic programs. We also introduce dynamically proving termination and non-termination of heap manipulating programs. Thank you for your attention, and I'm happy to answer your questions.